Today we're taking apart one real reference architecture, an event-driven order processing system on Azure. Picture an online store where a customer places an order and behind the scenes a dozen things have to happen. Inventory checks, payment, shipping, notifications. Doing that with synchronous calls couples everything together and falls over under load. So we'll dissect an event-driven design that decouples it. By the end, you'll know which Azure messaging service does what, how a single order flows end-to-end, where this design breaks, and the trade-offs the architect actually weighed. Let's draw it. Here's the full diagram, bottom to top. At the edge, an API, Azure API management, accepts the order and writes it as an event. Above that sits the messaging layer, where most of the design decisions live. Azure Event Grid for reactive routing, Azure Service Bus for reliable commands, and Azure Event Hubs for high-throughput telemetry. On top, Azure Functions and Container Apps act as the consumers that do the real work. And underneath it all, Azure Cosmos DB holds order state, while Application Insights gives us tracing across the whole thing. The key idea: each layer can scale and fail independently of the others. The most common mistake is treating these three services as interchangeable. They aren't. Event Grid is for discrete events, things like order created with push delivery, fan out to many subscribers, and built-in retry. Service Bus is for commands and workflows that need ordering, sessions, transactions, and guaranteed first-in, first-out delivery, things like charge this payment exactly once. Event Hubs is a streaming ingestion pipeline built for millions of events per second, partitioned with consumers reading at their own pace, ideal for clickstream or device telemetry. As a rule of thumb, events that announce use Grid, commands that instruct use Service Bus, firehose data use Event Hubs. Let's trace a single order. The API writes an order-created event to Event Grid. Grid fans it out to subscribers, an inventory function reserves stock, and in parallel a function drops a payment command onto a Service Bus queue. A payment processor consumes that queue with sessions enabled so messages for one order stay ordered, charges the card, then emits a payment completed event back to Grid. That triggers shipping and a notification function. Notice nothing blocks anything else. Inventory and notifications run concurrently, and each stage persists its result to Cosmos DB, so the order state is always reconstructible. Now the failure modes, because async systems fail in subtle ways. First, duplicate delivery. Event Grid and Service Bus both guarantee at least once, not exactly once, so a consumer can see the same event twice. Your handlers must be idempotent, typically by storing a processed message ID in Cosmos and checking it. Second, poison messages. A payment that keeps throwing will retry forever unless you cap delivery attempts and route it to a dead letter queue for inspection. Third, ordering gaps. Without Service Bus sessions, 2 updates for one order can land out of order. And fourth, backpressure. If a downstream function can't keep up, messages pile up, so you watch queue depth and scale on it. So why this shape? The architect traded simplicity for resilience. A synchronous chain is easier to reason about and debug, but one slow dependency stalls the whole order. Going event-driven buys independent scaling and fault isolation, at the cost of eventual consistency and much harder debugging, which is exactly why distributed tracing through Application Insights is non-negotiable here. They also chose managed services over self-hosting Kafka. Event Hubs speaks the Kafka protocol, but removes the operational burden. The honest downside is that you now reason about partial failures and idempotency everywhere. For a high-volume system that's worth it, for a low-traffic internal tool, it's over-engineering. One layer deserves a closer look: observability. In a synchronous app, a stack trace tells the whole story. Here, a single order touches the API, Event Grid, 2 queues, and 4 functions, so you need a correlation ID that rides along on every message and links every span. Application Insights and the broader Azure Monitor stack stitch those spans into one end-to-end transaction. Pair that with metrics on Service Bus queue depth and dead letter counts, and alerts when either crosses a threshold. Without this, a stuck order is nearly impossible to diagnose. Treat tracing as part of the architecture, not an afterthought. To recap, pick your messaging service by intent: Event Grid for announcements, Service Bus for ordered commands, Event Hubs for high-volume streams. Make every consumer idempotent, dead letter your poison messages, and bake in correlation-based tracing from day one. The trade-off is real. You gain resilience and scale, but pay in eventual consistency and debugging complexity. Your one concrete takeaway: before adding any consumer, write down its idempotency key and its dead letter policy. If you can't, you're not ready to deploy it. Service quotas, throughput tiers, and pricing on these services change often, so confirm the current numbers in the Azure docs before you commit to a design. If this helped, do me a favor, hit the like button, subscribe, and tap the bell so you don't miss the next one. See you in the next video.